Your plain old telephone and the pair of copper wires connecting it to your local exchange constitute one small element of a global telecommunications network of astonishing scope and complexity. The Public Switched Telephone Network, or PSTN, is a vast array of conventional phone lines, fiber optic cables, microwave links, communications satellites, and undersea cables interconnected at exchanges using standardized communications protocols and fully integrated with cellular networks and the internet. Thanks to this vast network and the international standards that ensure consistent transmission of information across it, your phone can connect with any other telephone in the world in a matter of seconds. In today's lecture, we'll begin by looking at how the PSTN operates as a communications network, in contrast with other types of networks like the internet. We'll then examine the key transmission media and technologies that constitute the PSTN, and we'll see how the ongoing digital communications revolution is changing this system even as we speak. Now, there are two basic types of telecommunications networks: circuit switched and packet switched. In a circuit switched network, information is transmitted through a dedicated communications channel from one terminal through one or more intermediate nodes to another end station. The connection must be fully established end-to-end before the transmission can begin, and then it's released after the transmission is complete. Circuit switch communications are characterized as continuous, exclusive, and temporary. Continuous because once the connection is established, it's maintained for the duration of the call. Exclusive because the channel isn't shared with any other users during the transmission. And temporary because the connection only exists for the duration of the call. The quintessential example of a circuit switched network is the public switched telephone network. In the PSTN, the terminals are usually telephones and the nodes are switches located at the local, tandem, and toll exchanges. As we learned in our last lecture, the switch was once a human plugging wires into a switchboard manually. But today, the term switch refers to a specialized computer that's used to establish connections between transmission lines. A fundamental characteristic of the PSTN is that the switches are smart so that your telephone doesn't have to be. When you dial a phone number, it's the switches that figure out the optimum path through the network to your recipient, taking into account the current level of traffic and working around any trunks or switches that are currently out of service. It's the switches that generate dial tones, ringtones, call waiting, and busy signals. And it's the switches that establish and later release your connection. All this so you can use a simple telephone with no processing power of its own. The principal advantage of the PSTN's circuit-switched architecture is quality of service. Once the connection is established, there's minimal latency or delay, so the system is optimal for real-time voice traffic. The disadvantage is relative inefficiency, resulting from the fact that most phone conversations actually consist of approximately 50% silence when we pause to gather our thoughts, take a breath, or wait for the other party to respond. As such, that dedicated communication channel is usually operating far below its capacity. This limitation is ingeniously addressed in the packet-switched network, a fundamentally different network architecture that's the basis for the internet. In a packet-switched network, a transmission, which might be voice or data, is broken up into many small chunks called packets, which are then transmitted independently across a shared network, with each packet potentially following a different route. At the network nodes are devices called routers, which receive packets and forward them onward through the network. Each packet incorporates a header containing two key pieces of information: the address of the packet's destination and a sequence number, which is ultimately used to reassemble the packets in the correct order at their destination. At each node, the router processes packets independently on a first-in, first-out basis, determining only the next node in each packet's journey. This determination is based on a routing protocol that typically attempts to minimize the number of nodes along the remainder of the path. All transmission lines in a packet switch network are shared, so packets originating from many different sources are constantly arriving in the queues of the routers. During periods of heavy traffic, these queues can cause considerable latency or delay. And if any queue exceeds the storage capacity of its associated router, the overflow packets are simply lost. That's why sometimes that web page never finishes loading. The major advantage of packet switching is that it's highly efficient use of network resources. In comparison with a circuit switched model, packet switching also represents a decentralization of intelligence from the core of the network to its outer periphery. Internet routers don't need to be as smart as PSTN switches because processors at the source and the destination do most of the heavy lifting, creating and addressing the packets and then reassembling them after transmission. This characteristic, decentralized intelligence, enhances the system's redundancy and resilience while also enabling the Internet's most characteristic feature, its capacity to grow and change in creative new ways, seemingly on a daily basis without any centralized control. The disadvantages of packet switching, latency and data loss, reflect the fact that the Internet was originally designed for the efficient transmission of so-called bursty data. That is, data sent in short spurts, separated by long periods of inactivity. Email is a perfect example of bursty data. While you're reading a message, thinking about it, and composing a response, no data are being transmitted. Then you hit send and launch all those packets within a fraction of a second. Packet switching is ideally suited for this sort of communication. Today, however, we're demanding much more from the Internet. Streaming video, voice over IP telephone service, interactive online gaming, communications that are anything but bursty. And the Internet is changing to accommodate these demands. But it's changing in ways that are far beyond the scope of this particular course. The PSTN, on the other hand, was designed and optimized for transmission of the human voice. So before we examine the technologies underlying the PSTN, we should talk a bit about the human voice and its representation in both analog and digital communications. This is my voice, displayed in real time as an analog waveform. Now what you're really seeing here is a graph of volume versus time. And as we zoom in on that graph, we see that it's actually a series of irregular waves, which makes sense, since we know that sound propagates in waves. We also know from our discussion of alternating current in an earlier lecture that all wave phenomena can be characterized by a few key parameters. The maximum height of the wave is its amplitude, and for a sound wave, the amplitude corresponds to volume. A larger amplitude corresponds to a louder sound. The time required for one full cycle is called the period, and 1 divided by the period equals the frequency, expressed in cycles per second or hertz. For a sound wave, the frequency corresponds to the pitch. Low frequency, high frequency. Now, how do these parameters apply to my voice? Well, here the waveforms are quite irregular, but we can still discern sinusoidal cycles. Here, for example, this wave has a period of 0.0002 seconds. Thus, the frequency is 1 divided by 0.0002 equals 5,000 hertz, which is a very high D sharp. But this snippet of my voice is actually dominated by a larger waveform, 10 times longer, with a frequency of about 500 hertz. That's the B above middle C. As you can see, our voices are actually a mix of waveforms with varying frequencies. Indeed, the human voice can generate frequencies from about 100 to 10,000 hertz. Now, anytime we express a range of frequencies in this way, we're defining a bandwidth. Thus, the bandwidth of the human voice is approximately 10,000 minus 100 equals 9,900 hertz. However, most of the sounds that constitute intelligible speech fall within a much narrower range, from about 250 to 3400 hertz. And so communications channels that are intended for transmission of the human voice are typically allocated a bandwidth of 4000 hertz. Voice transmissions can take either of two forms, analog or digital. In the modern PSTN, most voice signals start out as analog in the local loop, are converted to digital for transmission through the core, and then are converted back to analog for the last mile to the recipient. We've already seen analog transmission in our discussion of plain old telephone service in the last lecture. When pressure waves propagating from my vocal cords encounter the microphone in my telephone, these continuous variations in volume are converted into similar variations in both electrical current and voltage, which then propagate through the subscriber line to my local exchange. Digital transmission is a bit more complicated because it requires that we represent this irregular continuous waveform as a series of ones and zeros. To accomplish this, we're going to sample the waveform at regular intervals of time, and because the bandwidth of the voice transmission will be 4000 hertz, we'll sample at twice that rate, 8000 samples per second, to ensure that we adequately capture the variations in amplitude and frequency. At each of these points, we measure the voltage of the voice signal and represent it as an 8-bit number. Okay, so what's a bit? A bit is the basic unit of information in digital communications and computing. It can have only two possible values, 1 or 0. And so for our 8-bit number, each digit can be either 1 or 0. Two possible values for each digit means that the total number of possibilities is 2 times 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 2, or 2 to the 8th power, or 256. And each of these numbers corresponds to a level of voltage in the voice signal. Thus, my digitized voice is actually a series of 8-bit numbers, each representing the volume of my voice at an instant in time, measured and sent down the line 8,000 times every second. The resulting rate of data transfer, called the bit rate, is 8 bits per sample times 8,000 samples per second equals 64,000 bits per second. Now, what we've just done is to define the standard voice channel used in the PSTN, a bandwidth of 4,000 hertz and a bit rate of 64,000 bits per second. This specification, which is known as DS0 in telecommunications lingo, is a very powerful metric for understanding and comparing the capabilities of transmission media used in the PSTN. The transmission medium that was once used throughout the PSTN is this pair of twisted copper wires. Today, most of the copper in the core of the network has been replaced by transmission media with far greater capacity. But as we've seen, the twisted pair is still used extensively in the local loop of the plain old telephone service. And this is hardly surprising, since copper wires are both less expensive and easier to work with than all of the alternatives. Copper cable has a usable bandwidth of about 1 million hertz and can move data at a bit rate of 2 to 3 million bits per second. But impressive as these numbers might sound, they pale in comparison with other transmission media. And beyond their limited capacity, copper wires suffer from severe signal attenuation, which causes the signal to get weaker over a very short distance, and high susceptibility to noise and interference, which introduce errors into the data stream. In the local loop of the PSTN, these limitations are addressed simply by locating local exchanges or concentrators within about 2 miles of the subscribers that they serve. But in a long-distance trunk, the only way to compensate for signal attenuation is to place amplifiers at approximately 1 mile intervals along its length. Now, an amplifier uses externally supplied energy to boost the power of an input signal, and then it sends the amplified output signal on down the line. The amplifier was invented in 1906, and its first practical application was to facilitate long-distance telephone transmission. These early amplifiers used vacuum tube technology, which remained in vogue until the transistor was invented in 1947. Interestingly, vacuum tube amplifiers are still used in certain specialized applications, like satellites, as we'll learn in our lecture on satellite communications. And because amplifiers work in only one direction, the core of the PSTN was developed with 4-wire circuits, rather than the 2-wire configuration of your local loop. When we have a conversation over a 4-wire circuit, my half of the conversation travels in one pair of wires, and your half goes the other direction in the other pair. Recognize, however, that in modern inter-exchange voice transmissions, you'll never actually have one set of wires all to yourself. Various types of multiplexing are used to squeeze many simultaneous calls into one circuit. The original type, called frequency division multiplexing, was actually invented before the telephone for use in telegraph systems in the late 19th century. And because it's best suited for analog transmission, this was the principal form of multiplexing used in the PSTN until the system's digital transition in the mid-20th century. In frequency division multiplexing, the total bandwidth available for transmission is subdivided into a series of non-overlapping frequency subbands, each of which constitutes a separate communications channel. For each of these bands, an electronic oscillator is used to create a carrier signal with its frequency at the center of the band. This carrier frequency is always significantly higher than the frequency of the voice signals that are being transmitted. Within each band, the carrier and voice signals are then electronically mixed through a process called modulation. There are several different types, but the most common are amplitude modulation and frequency modulation. In amplitude modulation, the amplitude of the carrier signal is modified to match the amplitude of the voice signal, like this. In frequency modulation, the frequency of the carrier wave is modified to represent the voice signal. In both cases, the effect is to piggyback the voice signal onto the carrier signal for each channel. All channels are then transmitted simultaneously through a single circuit and sorted out at the destination by sending the combined signal through a bank of receivers, each tuned to a different frequency. The individual channels must be demodulated by subtracting the carrier signal from the modulated signal to reconstruct the original voice signal. And by the way, just in case you haven't figured it out yet, amplitude modulation and frequency modulation are also used for AM and FM radio transmission. Indeed, the familiar concept of broadcast radio can really help us understand the somewhat less familiar concept of multiplexing. In radio, the electromagnetic signals transmitted by many different radio stations are all simultaneously impinging upon your radio's antenna. But by tuning your receiver to the frequency of one specific transmitter, you can isolate that particular signal from all the others. Broadcast and cable television work essentially the same way. For telephone, only 24 conversations at most can be multiplexed onto a standard 4-wire copper circuit. Beyond that, the higher frequencies required for multiplexing cause excessive power loss. This limitation was overcome with the development of coaxial cable. Now, you'll recognize this stuff as the cable used for cable TV. But it was actually developed in the 1920s as a replacement for twisted pairs in the inter-exchange trunks of the PSTN. Coaxial cable, or coax, consists of a heavy copper core surrounded by an insulating plastic sheath, a woven metal shield, and an outer protective jacket. In a circuit, the copper core serves as the conductor and the woven shield as the return path. The great advantage of this arrangement is that the electromagnetic field generated by the conductor is largely confined within the shield, resulting in less power loss and greater resistance to interference. Standard coax also can support a bandwidth of 370 megahertz. That's 370 times more than a twisted pair. And when used with frequency division multiplexing, a pair of cables can carry 13,200 of those standard DS0 voice signals simultaneously. Still, the use of coax is severely constrained by the need for amplifiers spaced at roughly 1.5-mile intervals along the transmission lines. This limitation led to a new technology, microwave communications, developed originally for military applications during World War II, and subsequently deployed into the core of the PSTN as a replacement for coax on long-distance trunks. A microwave is a form of electromagnetic radiation, a very high-frequency radio wave, which can be focused into a narrow beam and used for point-to-point communication. We'll discuss the electromagnetic spectrum in greater detail in the next lecture when we examine cellular technology. For now, suffice it to say that microwaves provided a substantial improvement over coax in terms of both capacity and flexibility of deployment. The most recently deployed analog microwave systems can transmit 61,800 two-way voice signals simultaneously. And more importantly, microwaves attenuate far less rapidly than electrical signals transmitted through copper, though they are susceptible to degradation by rain and fog. Still, at the frequencies used for phone transmissions, microwaves can reliably transmit 25 to 30 miles. In the PSTN, a microwave trunk consists of a chain of tall towers like this one, which serve as relay stations at 25 to 30-mile intervals. Microwave transmission requires direct line of sight from transmitter to receiver, which is why the towers are always tall and usually located on high ground. At the top of each tower, directional antennas are arranged in pairs to facilitate two-way transmissions, and for each pair, there's usually another pair pointing in the opposite direction. Incoming microwave signals are received, amplified, and then retransmitted onward to the next tower, like this. Now today, microwave trunks in the PSTN have mostly been replaced by fiber optic cable. Yet microwave remains quite valuable for situations where stringing cable can be problematic, for crossing deserts or mountainous regions, and for connections to remote locations like islands. The microwave band is also used for satellite communications, an application for which cables of any kind aren't particularly helpful. And today, this technology is finding all sorts of new applications in private commercial point-to-point communications over relatively short distances, as illustrated by this directional antenna on this hospital roof. In the latter half of the 20th century, the PSTN was gradually converted from entirely analog to mostly digital. There were two principal drivers for this transition. First, analog signals are far more susceptible to loss of fidelity than digital signals. Any signal is degraded as it's transmitted, in part because it attenuates or gradually loses power, but also because it's corrupted by noise, which might result from moisture in a cable, dirt on an electrical contact, or any number of other causes. In analog communications, attenuation is mitigated by periodic amplification, as we've seen. The problem is that an amplifier can only increase the power of the signal. It can't remove the noise. Indeed, an amplifier actually amplifies the noise right along with a signal, and even adds some internal noise of its own. Thus, noise accumulates throughout the transmission, and because there's no way for the receiver to distinguish between signal and noise, errors are introduced into the transmitted information. Digital signals also lose power and accumulate noise during transmission, but because a digital signal consists entirely of discrete on-off pulses representing ones and zeros, it's much easier to distinguish between the signal and the noise. This is accomplished by a device called a regenerative repeater, which is used in lieu of an amplifier in digital systems. The repeater examines the signal, determines whether each bit was supposed to be a 1 or a 0, and then it regenerates a new noise-free signal and sends it on to the next repeater. Because the signal is regenerated at each repeater, noise doesn't accumulate. Thus, the very nature of digital data allows for long-distance transmission with substantially fewer errors. The second major reason for the analog to digital conversion of the PSTN is that digital communications are well suited to a fundamentally different and more powerful type of multiplexing called time division multiplexing. To illustrate how this system works, let's assume that 4 phone conversations, which we'll label A, B, C, and D, will be multiplexed together. Recall that when we digitized my voice a few minutes ago, we sampled the analog waveform 8,000 times per second and generated an 8-bit chunk of data for each sample. In time division multiplexing, each chunk of data from all 4 conversations is fed sequentially into a single transmission, like this, with each conversation having its own assigned time slot. This simple example has 4 channels, but the US baseline standard for time division multiplexing uses 24 channels per circuit, and inter-exchange trunks often use 4,000 or more. So let's pause for a moment and reflect on what this really means. When I make a long-distance phone call, my conversation is being broken up into tiny pieces at 1/8,000th of a second intervals, interwoven with similar pieces of at least 23 other people's conversations, sent through a wire as a series of on-off pulses representing ones and zeros, and then at the other end, miraculously reassembled into a reasonable reproduction of my voice and then sent as an analog signal over the local loop to my recipient. It is really quite a remarkable process. But in the modern world of telecommunications, nothing is more remarkable than optical fiber. First deployed in 1979, fiber optic communication involves the transmission of a digitally encoded light beam through a tiny fiber of glass. The digital encoding is accomplished by a computer-controlled laser, which sends pulses of light through an optical fiber to represent ones and zeros. The actual fiber optic cable looks like this: an inner core of ultra-pure glass, less than 1/2000th of an inch in diameter, surrounded by a glass cladding with slightly different optical properties. The cladding then serves as a light pipe, containing transmitted light within the core by reflecting it off the boundary between the 2 layers, as you can see here. Outside the cladding are a plastic coating, which prevents the fiber from bending excessively, a layer of Kevlar for strength, and an outer protective jacket. Thanks to these protective layers, optical fiber can be suspended from utility poles, buried, and even used underwater. And by the way, whenever you see these gadgets on an overhead line, you can be sure you're looking at a fiber optic cable. Called thimbles, they're used to store excess cable so that if a transmission line ever breaks, there's enough extra length available to fix it with a single splice. And here's another clear indicator that you're looking at a fiber optic line: elaborate rigging to ensure that the cable doesn't turn any sharp corners that might damage the glass fibers. The performance of optical fiber as a transmission medium is simply mind-boggling. Not only is its rate of attenuation so low that repeaters are typically needed only every 500 miles, not only is optical fiber immune to electromagnetic interference, but each of these tiny strands of glass, only slightly larger in diameter than a human hair, can comfortably carry 40 gigabits per second. That's 40 with 9 zeros after it, the equivalent of over 600,000 simultaneous digitally multiplexed phone conversations. And with new advanced multiplexing methods currently being fielded, that number grows to about 3 million conversations. Imagine the entire population of Chicago placing phone calls simultaneously through one single fiber. It's no wonder that copper, coax cable, and microwave have been rendered largely obsolete by this technology. Today, optical fiber has sparked a communications revolution while fundamentally changing the PSTN. No doubt, the public switched telephone network of today is a very different animal from the PSTN of 1950. Back then, simple analog signals were transmitted over twisted copper wires and routed through manually operated switches. Today, the system is digital throughout its core, entirely automated and vastly more diverse in terms of both transmission media and the kinds of information transmitted through those media. Today's PSTN is also thoroughly integrated with the internet. To a large extent, both systems run on the same public infrastructure. And many of us access the internet through our telephone subscriber lines. Yet the thing I find most fascinating about the PSTN of today is that despite these revolutionary developments, so many of the technologies that were part of the system when I was a kid, microwave, coax, the landline telephone, are still viable parts of the system today. The PSTN is an impressive technological achievement from many perspectives, but perhaps the most important of all is the fact that it integrates so many fundamentally different modes of communication and such a broad range of technological sophistication, yet it still operates with such a high level of reliability. In our next lecture, we'll look at a particularly important mode of communication that is integrated within the PSTN, the cell phone. The cellular telephone is a major part of the ongoing telecommunications revolution. The ubiquity of this device has changed our lives in profound ways. And for this reason alone, we should know something about the underlying technology. I'm sorry. But cellular technology is also worth knowing about because it's often more problematic than the other technologies in our lives. Why do I get good service in some areas and bad service in others? Why do I sometimes lose my connection for no apparent reason? Why does my battery consumption seem to vary so wildly? Why did they build that ugly antenna tower in my backyard? Well, as you know, I'm a strong advocate for being an informed user of technology. Today, I hope you'll come to recognize that being an informed user of cellular technology can be particularly beneficial. At the most fundamental level, cellular communication involves analog or digital encoding of a radio carrier signal. Thus, we can't understand the technology without first understanding radio. Anytime electrons move at varying speed, they generate electromagnetic radiation that propagates through space at the speed of light. We've seen this phenomenon before. The reason twisted copper wires are twisted is to reduce the adverse effects of electromagnetic radiation emanating from the wires as current flows through them. Coaxial cable uses a metal shield to contain the electromagnetic field within the cable and to protect against electromagnetic interference from outside. Because electromagnetic radiation oscillates as it propagates through space, it's characterized as a wave phenomenon. And like any wave phenomenon, it can be classified according to its frequency. The electromagnetic spectrum, with its associated frequencies, is illustrated here. At the bottom end is low-frequency, long-wave radio. The progressively higher frequencies are conventional radio, including the frequency bands used for AM and FM radio, then microwave, infrared, visible light, ultraviolet light, X-rays, and gamma rays. By the way, these low-frequency radio waves are called long waves because the physical length of a wave is inversely proportional to its frequency. The 30 Hertz radio waves used by the US Navy to communicate with submarines are over 6,200 miles long. FM radio waves, transmitted at 100 megahertz on your FM dial, are about 10 feet long. Microwaves at 10 gigahertz are about 1/100th of an inch long, so small that they can be scattered by raindrops, which explains why microwave communication signals can be degraded by rain and fog. In general, electromagnetic waves with low frequency can travel much farther than those on the opposite end of the spectrum, but they have significantly lower capacity for carrying information. Electromagnetic waves with high frequency have far greater capacity by virtue of their greater bandwidth, but they also attenuate more quickly. And as we've seen with microwaves, their waveforms are so small that they're highly susceptible to atmospheric interference. For these reasons, most wireless communications use the middle of the electromagnetic spectrum. Mobile phones generally operate primarily in the frequency band just above FM radio, from about 700 to 2500 megahertz. So, how does radio communication work? Well, in general terms, a transmitter generates an alternating current that's been modulated or electronically mixed with a signal representing the information that's being transmitted. This alternating current is passed through an electrical conductor called an antenna. And because the current is oscillating, it generates electromagnetic waves at the same frequency as the current. These waves radiate off the antenna into space at the speed of light. As long as the frequency of the alternating current is in the radio frequency range, the resulting electromagnetic waves will be radio waves. At the other end of the transmission, the process happens in reverse. The electromagnetic waves impinge upon the receiving antenna, introducing a corresponding electrical current. This signal can then be demodulated to retrieve the transmitted information. Now, antennas can be designed to transmit and receive in all directions, like this one on my walkie-talkie. Or they can be designed to focus electromagnetic waves in a particular direction, as we saw with the directional antennas used on microwave relay stations last lecture, and as we'll see with parabolic satellite dishes in the next lecture. And so we come to the cell phone, which is really just a radio transmitter receiver. In this sense, the cell phone isn't really new technology. It's not fundamentally different from those walkie-talkies we see in the World War II movies, with two exceptions. First, a walkie-talkie typically operates on only one radio frequency, so you can either transmit or receive at any given time, but not both. Most cell phones operate on two frequencies to facilitate simultaneous transmission and reception, called full duplex communication. Now, I say most because a recent technological innovation actually allows simultaneous two-way communication on a single frequency, as we'll see later in this lecture. Second, those original walkie-talkies were all analog devices. And while the first generation of cell phones was analog as well, all modern mobile devices encode and transmit information digitally. Although the cell phone itself is conceptually similar to a simple walkie-talkie, what makes cellular networks so complex is the need to handle millions of conversations simultaneously. The electromagnetic spectrum is a finite resource. If we start handing out two frequencies per mobile phone, we'll run out of frequencies long before we run out of mobile phone users. Cellular networks handle this challenge through a concept called space division multiplexing. A geographic region is subdivided into a regular grid of smaller areas called cells. And yes, that's why it's called a cellular system. Each cell has its own antenna and base station. Taking a hint from nature, these cells are normally hexagonal, like the cells of a honeycomb, to provide efficient coverage with minimal overlap. Within each cell is a base station, which incorporates the radio transmitters, receivers, and antennas that communicate with all mobile devices located within the cell. The power of the radio transmitter is deliberately limited so that frequencies can be reused in other cells without causing interference between transmissions. But which other cells? The answer to that question depends on a factor called the cellular reuse pattern. The first generation of commercial cellular technology was launched in Japan in 1979 and called 1G for first generation. In this system, each cell was about 8 miles wide, and the cellular reuse pattern was 7, meaning that each cell of this 7-cell module used a completely different set of frequencies. Now, when we replicate this reuse pattern across the countryside, we see that it always provides a buffer of 2 cells between any pair of cells using the same frequencies. For example, any 2 yellow cells have 2 non-yellow cells between them in any direction. Now, the electromagnetic spectrum is a highly constrained resource, and so it's tightly controlled by government regulatory agencies like the U.S. Federal Communications Commission. In 1G networks, the FCC typically allocated enough radio spectrum to provide each service provider with 832 voice channels. That is, 832 discrete frequencies that could handle simultaneous voice communications without interference. 832 channels allow for half as many two-way conversations, or 416. With a cellular reuse pattern of 7, these channels had to be allocated equally among the 7 cells in each module. As a result, each of those 8-mile diameter cells in the 1G system could serve 416 divided by 7 equals 60 simultaneous conversations. Accommodating 60 phones within an 8-mile diameter was a revolutionary capability back in the 1980s. Today, it probably wouldn't even be good enough to qualify as inadequate. And so, the history of cellular technology development since then has revolved around the need to handle an ever-increasing number of users, demanding ever more bandwidth for both voice and data communications, and ever more reliable and responsive service. One response to these challenges has been simply to use more efficient cellular reuse patterns. For example, this one is based on a 4-cell module, which still provides a buffer of 1 cell between each pair of cells operating on the same frequencies. This simple change allows for the use of 75% more frequencies per cell, with a corresponding increase in the number of users. However, the smaller buffer between the common frequencies also requires the use of antennas with more precise control of their coverage areas to minimize the likelihood of interference. One common technique for achieving better coverage has been to place the antennas not at the center of each cell, but rather at 3 of the corners, like this. With this configuration, directional antennas are now used to limit each tower's coverage more effectively to the assigned cell. Note also that in this configuration, each cell is served by 3 different towers, providing more uniform coverage, and each tower covers 3 different cells. And that's why, at the top of most cell towers, you'll find triangular arrays of directional antennas like this one. Each side of the triangle is covering a different cell. And viewed from a different angle, we can see that each antenna is angled slightly downward here to ensure that transmissions don't overshoot the cell and cause interference. Another response to the need for greater capacity has been to use smaller cells in areas where larger numbers of users are congregated. The capability to subdivide big cells into little ones like this was an important new feature of the 2nd-generation cellular network standard, or 2G, which was first deployed in 1991 in Finland. Since then, we've seen the establishment of microcells, each about a mile wide, picocells, typically 500 feet or less, and even femtocells on the order of 30 feet. Now, picocells and femtocells are often used to extend cell coverage indoors, the former for office buildings, shopping malls, train stations, and similar large public facilities, the latter for small businesses and even individual homes. Beyond the improved coverage, smaller cells also have the advantage of requiring less power at the base station and in your phone. And yes, today, most cell phones do have variable power output, and the cellular base station actually controls your phone's power level to maintain an adequate signal while minimizing drain on your battery. But this relentless subdivision of cells has some significant downsides too. Obviously, one is the added cost of more antennas, more base stations, and more network interconnections. Evidently, this cost is being met by the ever greater number of subscribers that these smaller cells are serving. So perhaps it's not a significant issue. But a much more significant drawback of smaller cells is a larger number of handoffs, which occur every time a user moves from one cell to another. We'll talk about how handoffs work shortly. For now, it's only important to recognize that the handoff is a complex process requiring considerable computation and information exchange between your phone and the cellular network. Consequently, demanding too many handoffs in too short a period of time can cause problems. Often this challenge is addressed by using macro cells, sometimes as large as 20 miles across, in rural areas and along highways where users are most likely to be crossing from cell to cell at higher speeds, and by using smaller cells in areas where people are likely to remain in one cell for relatively longer periods of time, like shopping malls and office buildings. But what happens when a highway runs right through the middle of a densely populated metropolitan area like this? In such situations, many modern cellular networks use umbrella cells, which provide redundant wide area coverage overlaid onto a grid of smaller cells. In this arrangement, when a microcell detects a mobile device moving at very high speed, it hands off the call to the umbrella cell, thus significantly reducing the subsequent number of handoffs. Allowing the use of variable cell sizes contributes significantly to enhanced capacity in second generation or 2G cellular networks. But the most important contributor by far was the change from analog encoding in 1G to digital encoding in 2G. This change allowed for the encryption of voice transmissions, addressing a particularly serious security concern with wireless communications, and it opened the door to the transmission of data as well as voice. Text messaging, officially the Short Message Service or SMS, was an integral part of the 2G standard, and it paved the way for the smartphones of today. But most importantly, the switch from analog to digital allowed for significantly more efficient use of the limited electromagnetic spectrum assigned to cellular communications because it incorporated multiplexing, or to be more precise, it incorporated more sophisticated forms of multiple access. So what's the difference between multiplexing and multiple access? In 1G networks, the simple system of allocating two frequencies to each user is called frequency division multiple access. The concept is quite similar to frequency division multiplexing, which we discussed last lecture in the context of wired networks. But there's a subtle difference. In multiplexing, multiple conversations are combined into a single signal for transmission through a wire. In a wireless network, the individual conversations are transmitted independently between various mobile devices and the cellular base station. This is multiple access. The major technological advance in 2G networks was a new system called time division multiple access, which actually combines the concepts of frequency division and time division multiplexing. In time division multiple access, the entire available frequency spectrum is first subdivided into channels, as was done with frequency division multiple access. And then, within each channel, as many as 8 different phones are each assigned a specific time slot for transmission. The phones then transmit in short bursts within their respective time slots in rapid succession. Each cycle of 8 transmissions is so short that users perceive their conversations as continuous, even though they're actually a series of discrete samples. Now, by itself, time division multiple access provides an 8-fold increase in capacity over the simpler frequency division system used in 1G networks. But with increased capacity comes a significant new technological challenge: synchronizing transmissions by mobile devices located at different distances from the cellular antenna. Even though radio waves propagate through space at the speed of light, the time slots allocated to each burst of data are so small that the time it takes a transmission to travel across a cell can actually cause a given burst to miss its assigned time slot. To compensate for this travel time, the base station calculates something called a timing advance for each phone and sends that information to the device. The phone then sends its bursts of information just a little bit earlier by the amount of the timing advance, so they arrive at the antenna at precisely the correct moment. This system works well when the phone is standing still. But when the phone is in motion, there's typically some lag in matching the timing advance to the phone's actual position. Thus, to prevent interference, a small chunk of time needs to be inserted between the assigned time slots in the transmission sequence just to provide margin for error. And this added time robs some of the efficiency gain through time division multiple access. Now, this limitation has been very effectively addressed in third generation or 3G wireless networks, which were first deployed in 2001. Most 3G networks accommodate multiple users through a fundamentally different approach called code division multiple access, also called spread spectrum. In this system, there's no subdivision of the available spectrum into smaller frequency bands. Rather, all users within a given cell are communicating across the full spectrum at the same time. In this system, your mobile device modulates its original signal with a unique, randomly generated code that's provided by the base station. During this process, the bandwidth of the transmission is effectively spread across the full available spectrum, but it's done with a unique pattern that can be recognized and decoded by the receiver. Now, code division multiple access is very difficult to visualize, so let's try a simple analogy. Have you ever been in a foreign country, in a public place where lots of people are talking simultaneously in a language you don't understand? All you hear is a cacophony of unintelligible sounds. And then suddenly, you hear a single voice speaking in your own language. And as soon as you discern the unique and familiar pattern of speech in your own language, you're able to lock in on that single voice and filter out the undecipherable cacophony of the other voices in the room. This is the essence of code division multiple access. And in a cell network, this system uses electronic spectrum 10 to 20 times more efficiently than the simple frequency division scheme used in 1G networks. It also produces further increases in capacity by reducing the cellular reuse pattern to 1. In other words, the code division multiple access system allows for adjacent cells to operate on exactly the same frequencies without interference, as long as these adjacent cells use different codes. This feature represents another 7-fold increase in the number of users per cell in comparison with the reuse pattern of the 1G network. The efficiencies gained from this system arrived just in time to accommodate the explosion in demand for mobile connectivity that accompanied the introduction of the iPhone in 2007. But demand has only increased since then, as consumers have increasingly come to rely on their mobile devices for such functions as internet access, streaming video, gaming, voice over IP, mobile television, video conferencing, and cloud computing. To address these demands, enhanced 3G and recently introduced 4G systems have incorporated such features as advanced antennas that can transmit multiple parallel data streams simultaneously, data compression to pack more information more efficiently into a communications channel, duplexing techniques, which allow a single channel to share both the outgoing and incoming halves of a conversation, and new schemes for multiple access that, I must admit, are essentially indistinguishable from magic. All of these changes require an extraordinary level of coordination between the research and development community, government regulators, standards organizations, both domestic and international, wireless carriers, and hardware and software developers. And this challenge can only ever be met temporarily because demand is ever increasing and new technological paradigms are constantly emerging. The 5G standard is due out in 2020. Watch for it. It's hard to imagine a more dynamic and unpredictable context for technological development. Well, up to this point, we've discussed the radio communication link between your mobile device and the nearest cellular base station. But this is really only the tip of the iceberg. The base stations are just intermediate nodes in a far more extensive network of networks, illustrated here. Tens or even hundreds of base stations are connected to devices called base station controllers, which in turn are tied together by regional facilities called mobile switching centers. And by the way, the links between these base stations and controllers are usually landlines, but occasionally microwave links, as is the case with this particular station. The mobile switching center operates like a local exchange in the public switch telephone network. And indeed, it also provides the interface between the cellular network and the PSTN. The mobile switching center sets up and releases end-to-end calls, both mobile to mobile and mobile to PSTN. As the diagram indicates, Base station controllers are also connected to the General Packet Radio Service, a packet switched network that's overlaid on top of the circuit switched phone network and handles all internet data packets passing between your mobile device and the internet. Another critically important function that's performed jointly by the base station controllers and the mobile switching centers is the handoff of calls from cell to cell. Here's how this process works. Anytime you turn on your phone, it tunes into a specially designated frequency called the control channel, and it listens for something called a system identification number, which is broadcast by each base station to identify the associated cellular service provider. If your phone can't find a system identification number, it displays that annoying no service message. Your device knows the system identification number of its own service provider. So if it detects this number being broadcast, it knows it's operating within the coverage area of its own provider. If not, it's roaming within a different provider's area. On the same control channel, the phone then identifies itself to the service provider, and the mobile switching center stores the phone's location in a database. Through this mechanism, the system knows where your phone is located whenever it's switched on, so the associated mobile switching center can find you when someone dials your number. Now, when a call does come in, your switching center looks up your location in the database and then communicates with your phone over the control channel, sending you a ring signal and all the necessary coordinating information to complete the connection. For example, in a time division multiple access system, it provides the two frequencies and the time slots for transmission. In code division multiple access, it provides the code. When you answer the phone, you've got an end-to-end connection to the person who's calling you. Now, let's say that you're driving while the call is in progress. The base stations covering your cell are constantly monitoring the quality of your signal as measured by the signal strength, error rate, voice quality, and other metrics. When these measurements indicate that you're approaching the edge of your current cell, the base station controller, or in some cases the mobile switching center, coordinates with the adjoining cell, called the target cell, to effect a handoff. At the appropriate moment, your phone receives a signal on the control channel telling it to change frequencies, or in a code division multiple access system, to start using a new code. Once the switch is made, control of your call transfers to the target cell. In some systems, this changeover happens instantaneously. In others, there's a short period in which you remain connected to both cells and your phone can choose the stronger signal. In either case, the handoff is usually so precisely controlled that it can occur in the middle of a word and you won't notice it. But calls do occasionally get dropped during handoffs. When this happens, the most common reason is that the target cell doesn't have an open channel to give you. Now, in many ways, cellular communication is indicative of our love-hate relationship with technology. Even as we demand better coverage, better speed, and more wireless services, we staunchly oppose the construction of that ugly antenna tower in our neighborhood or on that picturesque hilltop out in the countryside. But not in my backyard really doesn't work very well with cellular networks. Coverage requires proximity to an antenna. And once the geometric grid is established, the corner of a cell falls where it falls. The cellular provider just doesn't have that much flexibility to move it around. Granted, competing service providers often exacerbate this problem by establishing their own independent systems of antennas. Thus, it's not unusual to see two cell towers standing on top of the same hilltop, like this. Fortunately, the level of conflict over this issue does seem to have abated somewhat within the past few years. These days, there seems to be less opposition to the construction of towers, perhaps because they've become so ubiquitous that we hardly even notice them anymore. And the service providers have done their part in exercising more creativity in the design and placement of their antennas. Consider just a few examples. It's now quite common to see cellular antennas grafted onto water towers and power transmission towers. Now, these installations are certainly no less ugly than standalone towers, but they are effective in concentrating ugliness in one location so that some other location might be spared. Particularly with the advent of microcells and picocells, it's now common to see cell antennas placed on the roofs of commercial buildings rather than on standalone towers. And in rural areas, well, you've got to love the antenna disguised as a stately pine tree, and in tropical climates, as a palm tree. These cellular cacti aren't terribly convincing, but they're a noble effort nonetheless. And here's my personal favorite. On the steeple of this beautiful old church in Poland, this antenna is perfectly disguised with trompe-l'oeil brickwork. Now that's an accommodation between aesthetics and technological necessity to which we can all aspire. Next lecture, we'll take wireless communications to a higher level with satellite communications.